Hello my YouTube followers. Today we're going to look at examples on Thevenin's theorem, and we're going to look at three examples. The first example being this question. So the question says use the Thevenin's theorem to find the current flowing through the 10 ohm resistor, which is the load resistor. So and how do we solve this? To solve this, we need to first of all remove the load resistor, and then from there we move on to finding the voltage across this open circuit voltage. So the first step is we go to finding the load. We remove the load resistor by creating what we call an open circuit. So the load resistor is removed, and then we can be able to start now finding the values. We can start finding first of all the open circuit voltage, which we can do by first of all finding the current, or using mesh analysis. You can use any applied method as we mentioned before. So in this case, you've got a node here which we could use or apply Thevenin's node analysis, or we could simply use mesh current method. So in this case, we create a mesh current like so, and then we use this mesh current to find the voltage across the 8 ohm resistor, and that is going to give us the value of the voltage VOC, or which we call the Thevenin's voltage, V Thevenin. So how do we go about that? A mesh. We create a one mesh circuit. So we've got the current here, which is I multiplied by 2. The sum of the voltage drops must be equal to the sum of the voltage sources. So we've got I multiplied by 8, and this gives us 10 volts. Because of the convention, the polarity here, the voltage is taken as a positive value. And if we group these together, what we simply have is the current I is equal to 10 divided by the sum of these two, which is 10 as well, giving us 1 amp. So this current flowing through the 8 ohm resistor is 1 amp, and therefore we can use that now to find the potential difference across the 8 ohm resistor, which is going to be the current multiplied by the resistance. So in this case is 1 multiplied by 8, giving us 8 volts, and that is the voltage across the open circuit. And this is then the voltage that we call the Thevenin's voltage, or the open circuit voltage. And then, having found that, we're able to now determine the value of the resistances, which is called the Thevenin's resistance. You could use also the voltage divider rule here to find the solution, meaning you just have, if we had to find the Thevenin's voltage using the voltage divider rule, then what we simply do is the voltage across the 8 ohm resistor is simply going to be equal to, we have the 10 volts, which is being shared by the two resistances. In this case, we have the 8 ohm resistor, which is over the ratio, the sum of the two resistances, 8 plus 2, and this multiplies by 10 volts, and this is going to give us 8 volts as well, which is the V Thevenin. So this is the voltage divider method that could be used as well. And then also you could use other methods. Nodal, for instance, could be used. Now let's come to finding the voltage across, the total resistance in this circuit for us to determine the Thevenin's resistance. So the circuit remains like so. What you have is the resistances, which is the 5 ohm resistor, you've got the 8 ohm, and you've got the 2 ohm resistor. Remember, we short circuit the voltage sources, so the voltage source has been short circuited. That's how we remove the voltage sources from the circuit. And then we look at the total resistance, or the Thevenin's resistance, far away from the load. So we're coming from this direction going towards where the load was. And you'll notice that the resistances, the 2 ohm and the 8 ohm, are in parallel. So our Thevenin then is going to be equal to the parallel resistances. That is, the 8 ohm is parallel to the 2 ohm, and that will be in series to the 5 ohm. So you find that by getting the 8 multiplied by 2 over the sum of the 2, which in this case is 10, and that adds to 5. And this gives you to have the total resistance in the circuit to be equal to 6.6 ohms. And that is our Thevenin's resistance. And therefore, we found the Thevenin's resistance. We know the value of the Thevenin's voltage. Then we can add back our load resistor, which we want to find the current through. So we know that the current that is going to flow through that circuit is going to be, in a nutshell, we can simplify the circuit to be, we have the total resistance that is in series with the voltage source, and this connects to the load. So you've got the load, and then we've got the total resistance, which was found to be 6.6 ohms, 6.6 ohms, and then you've got the total, or the Thevenin's voltage, which was found to be 8 volts, and this connects to the 10 ohm resistor. So to find the current through the 10 ohm resistor, then all we do is we get these two added together. So it's a voltage, which is the 8 volts, which is divided by the total resistance. In this case, the resistance is being in series, which is going to be 10 plus 6.6, and this gives us the current to be 0.482, and this is what we find as our final answer. So when we get back to our circuit, if you remember, you see that our final answer is 0.482 as shown here, and that is how we solve this problem. For the next example, we look at a Wheatstone bridge in this case, and for the sake of convenience, we are going to say that this is node A, and we're going to give this node as node C, and then we get this as node B, and this is as node D. So we've got to find the current that is flowing through the 32 ohm resistor, which is resistor 5, but we don't know which direction is flowing, whether it's flowing from A to B or B to A, and that we need to determine as well. So let's dig in and see how we find the solutions. So we're maintaining those letter symbols, and we're going to demonstrate what we do. So here I have drawn the circuits again, and I'm going to show the same lettering. We had A, B, and C, and D. So we continue the same. This is C, this is B, this is A, this is D. Now, what we've been asked is to find the current through the 32 ohm resistor, and for that reason, this is taken as the load resistor. So for us to find the Thevenin's voltage, or the voltage across the load resistor, we have to remove the load resistor, and this is what we have done. So we've removed the load resistor, and we remain with the circuit like so. And then we have to be able to determine now the voltage across this open circuit here. So we have to find VThevenin in here, and for us to be able to do that, we have to find the potential difference between A and B, and to make it easier, we have to determine the potential differences between each and every point. So the first one we start with is, let's start and find the voltage across A and C. So we call that VAC. So how do we determine VAC? VAC will be determined from taking this as the total voltage between C and D. So we're just looking at the voltage divider rule in this case, and that is, if we place it into an equation form, it is R1, then the sum of R1 plus R4. This is R4 here, and this must multiply by the total voltage. So in this case, we've got R1 is 2 and then R4 is 11. So 2 plus 11 here, and this must multiply by 54, and this gives us the voltage to be equal to 8.31 volts. That's the voltage between A and C according to the voltage divider. And we're also able to determine the voltage between B and C, in this case VBC, and this should be able to give us R2 divided by you've got R2 and R3 there as the denominator, plus R3, and that must multiply by E, and this must be able to give us, we've got 14 divided by 14 plus 3. This multiplies by 54, and this gives us 44.47 volts. And now, having found this, we have to find the potential between A and B. And for us to find the potential between A and B, we're going to get the difference between VAC and V, which is here, VBC. And that should be able to give us the potential difference between A and B. So the potential difference between A and B should be therefore be equal to what we found here between BC, which is 44.47, minus what we found here, AC, which is 8.31, and that must be able to give us 36.16 volts. And therefore, we know that the potential at C, because the polarity is here, this is 54 volts, we have got plus minus, meaning the polarity is plus, so this node here is at the potential of 54 volts. That's the potential at C. And therefore, we can be able to determine the potential between C and A, which is the voltage drop here, C and A, which we found to be 8.31 volts. So the voltage at A, then the potential at A here is then going to be equal to, so if we say the voltage at A, or the potential at A, must be equal to 54 volts minus 8.31, which we found as the potential there. And this must be able to give us the value of 45.69 volts. So that's the potential at A. And then, again, if you remember, between C and B, we mentioned that we've got a voltage drop of 44.47, and therefore we can also determine the potential at B, the voltage at B, at this value, or this node B, to be equal to 54 minus the potential difference between B and C, which in this case is giving us this value 44.47, and that leads to the value we obtain as 9.53 volts. Now that's the potential at B. Now, since the potential at A is known, and we know that the potential at A is 45.69 and is greater than the potential at B, which is also known, which is 9.53, the current therefore must flow in the direction AB. So current is going to flow from this direction to that direction, from A to B. If we determine the potential difference, we know the potential difference between A and B is simply 45 minus 5.3. That's the voltage across that. So, and we found that voltage to be 36.16. It's the same if you use the potentials AB, or if we use what we found here to be the potential difference between A and B to be 36.16 36.16. Okay, now if we are to find the resistance now, the total resistance, now you remember that this voltage source must be short-circuited. So when we short-circuit this voltage source, what we remain with is simply a line in between there. And if I'm able to show you this, it's going to appear as follows. So you've got what we had like so, and what is remaining is when we short circuit, so we're going to simply have a short circuit in between like so. And if you remember, we have 2 ohms, we've got 14 ohms, and we've got 11 ohms and 3 ohms. Our nodes are A, B, this is C, D. So what this tells us is that we've got a short circuit between C and D. This becomes one node. When this becomes one node, it simply tells us that this 2 is parallel to 11. In another way, we can show this circuit. It can appear as follows. So you have this short circuit there, and then you have a continuation. So this is one and the same. So if I'm to show, this will be node A, this is node B, and this is C and D, which has been short circuited. So you've got 2, 11, you've got 14, and you've got 3 ohms there. So the total resistance then in the circuit, or the Thevenin's resistance, which is the total resistance, is simply 2 and 11 parallel to each other, 14 and 3 parallel to each other, and then they'll be in series. So you've got 2 parallel to 11 plus 14 parallel to the 3 ohm resistor, and that should be able to give you 2 times 11 divided by 2 plus 11, and that adds to 14 times 3 over 14 plus 3, and this gives us 4.163 ohms, and that is now the total resistance, or the Thevenin's resistance in the circuit. And therefore the circuit now appears as follows. We have a resistor, which is the 4.163, and then to it is connected our source, which is now of value 36.16 volts, and to that is connected the load resistor, which we had removed earlier, and this value was 32 ohms. And now we're able to determine the current passing through this circuit and determine the current passing through this 32 ohm resistor, and this is going to give us the value to be equal to the source, which in this case is 36.16, divided by the total resistance, in this case 32 plus 4.163, and that gives us the value to be equal to 1 amp as the current passing through the 32 ohm resistor. So that is how we find the solution for this question. The third example in this circuit you see in Thevenin's theorem is asking you to find the current flowing through the 3 ohm resistor, which is this resistor here. And what we do is that we remove this resistor to find the potential difference at the open circuit, or what we call VOC. Now this question, I want my students and everyone out there to try it and find the solution. The only secret that I'm going to tell you here is that when we short circuit, when you're finding the total resistance, you short circuit the voltage source. What you're going to find is that when you short circuit the voltage source, the resistor, the 20 ohm resistor, which is this resistor, is also going to be short circuited. So you are going to have a circuit that is going to appear like so. So you've got the 5 ohm resistor, and then it continues. You've got the 10 ohm resistor, and then you've got the 1.67 resistor, and you've got an open circuit like so. So this, when you do the short circuit of the voltage source, this resistor is also going to be short circuited, and when the resistor is short circuited, there's no current, there's the is taken simply as a short circuit, just a wire. So your circuit then is going to be simplified to remain with only 3 resistances, and this is going to be your final circuit for finding the Thevenin's resistance. So what you are going to have here is the 1.67 ohm resistor, and then you are going to have that 5 ohm resistor will be this one, and then you have the 10 ohm resistor, and thereafter you find the total resistance. So that's the only thing that you have to understand here, that when there's a voltage source parallel to a current, to a resistor, and it is short circuited, then it is going to short circuit the resistor that is parallel to it. And that's the behavior of current, because all the current is going to flow through a wire of resistance, and therefore it will bypass this resistor and flow through that wire of less resistance. And basically that is it. And I would like you to put your answers in the comment section, which I'll be glad to see, and see who gets the answers correct. I'll not hint to what the values will be, but it will be nice to see your solutions solved and shared on the comment section. Thank you. Subscribe to my channel. See you next time.